at the end of the spring. Okay, so that's your setup. Let's say this mass is labeled m, so m is its magnitude, and let's say the spring is in its relaxed position. So at this point you can say that the spring doesn't have any potential energy because it's in the rest state, so you can define this to be x equal to 0 if you want, or x initial equal to 0 if you want. And then if I pull this, let's say I pull it to this point, let's call it point P, then obviously I have displaced the spring in this direction. So this would be the displacement rightward. And the force acting on this mass because of the spring would be leftward. So the force would be like that. Okay? So one of the things that we do is we write the force law associated with how the spring oscillates as Hooke's law. And the idea of Hooke's law is that the force F is minus kx. This minus sign is very important. So as you can see, more you stretch, the larger is the force. So if I am to plot x versus the magnitude of the force, I don't take into account the sign, then at x equal to 0, there is no force. X equal to 0 would be here. And then as I turn on x, the force will increase. And naturally, if I depict it like so, then the slope from the equation of a straight line y equal to mx, let's say, the slope will turn out to be the spring constant k, right? So, and the reason why I, again, put in F modulus is because I am not taking into account the presence of this minus sign here. So what does the minus sign tell us? The minus sign tells us that if I pull the spring to the right, this force will be to the left, because this force is a restoring force and it tries to bring it back. So the name of this force is a restoring force. So now what happens is that once I let it go, this thing is going to start to go towards the original position. And as it does so, it's going to speed up. And then what happens is, it won't stop here. It will overshoot. It will overshoot and end up the exact opposite amount to the stretch in the other direction. So this would be, let's say, my point Q. So the motion will go, so motion started here. It's going to start going back, it's going to speed up, and then the spring is getting compressed. As the spring gets compressed, the spring's energy increases, and it's going to now slow down because the spring is going to resist the compression. So you see, the displacement now is leftward, but the force exerted by the spring as the mass moves leftward would be rightward. And that would be consistent with F equal to minus kx, right? So once it goes this way, the restoring force would be backward. So that's very important. So this is the motion that I want you to be very, very clear on right now. It's very simple, provided you understand it, but it immediately gets out of control if you don't understand the concept clearly. So let us now look at a few things. First of all, if I let this thing go, then I'm releasing it from rest. If I release it from rest, at this point, the velocity at p, let's say, would be 0, right? Because I'm releasing it from rest. This is something that I'm imposing right now. It doesn't always have to be the case. I can release it anywhere I want. I can release it anywhere I want, in any way I want. I can give it a certain x, I can give it a certain v also, and pick a point somewhere. But this is a very special condition just to make our life simple. And this is called an initial condition actually, because it leads to initiation of the motion. So I've stretched it and I let it go. So the velocity at point P at time t equal to 0 would be 0. The maximum distance that I have pulled it before I let it go, that has a name, and this is called amplitude. So if it goes rightward, like we have right now, amplitude is A. If it goes leftward, amplitude would be minus A. The motion would be symmetric. What is the energy stored in a spring when we stretch or compress it? What is it called? Half what? So energy stored in a spring stretched by x or compressed by x. Compressed by x with respect to WRT, relaxed position. Relaxed position is at O. I didn't give it a name. PQ, let's call it O. Relaxed position O. Make sure you draw it correctly, because this drawing is very important. This drawing is setting the stage for what I'm going to do. So once again, we are starting at P. Again, that's a special initial condition. We are starting with this, the velocity at this point to be 0. We release it, it goes that way, it speeds up, and then it overshoots this relaxed position O. It comes here. Now it has squeezed the spring, and the spring hates it. The spring pushes it back, and it goes back, again speeds up, it goes there, and the oscillation continues. So that is your oscillatory motion that you have initiated with this special initial condition. It's a very physical problem, right? It's a very physical problem. So at this point, we want to understand a few things. So let me lay it out with a little bit more detail on the motion. Okay? So you're making me nervous, Rance. I just want to make sure that I'm recording correctly. Seems to be recording. So okay. So let us say I want to trace out what happens to this mass. So suppose I have this, right? This is O. I have stretched it. This is P, and this is where Q is going to be. Q. Oh, let me put it down. So Q. Okay. So if I now attach a chalk to this, and suppose there is a blackboard as it oscillates behind it, then I should be able to draw something like this. Suppose this is space, and you are getting a time trace. It's going to start here. So this is the position x. Let's say I'm plotting. So x is going to start off at this point. This is x equal to 0, relaxed point. This is the amplitude A, right? So x starts here, and x comes like that. You will find that it traces out a curve like that. Okay? It's not like this. Don't do something stupid like drawing a straight line here and here. People do that sometimes. Really makes me mad. Because the dumbest thing one can do it. That never happens in nature. So this thing starts off at 0 velocity, speeds up, goes there, comes back down. But this you are plotting is the distance. The distance that is being traveled. So this is x, if you will, as a function of t. Now, we can actually, by looking at this, by tracing it out, we can immediately define something called the period t. The period is the distance from crest to crest. Okay, so if I look at this oscillation over a longer interval of time, so just to be sure you understand, this axis is a time trace. So this is time. Starting here, as time progresses, it goes that way, comes out this way, and so on. Okay? But if I were to look at it over a longer time, it would be like this. Then crest, this is a crest, this is a crest, this is a crest. Crest to crest, the time taken is the period t. Alternately, trough to trough is also the period t. Alternately, from this point symmetrically to that point is also going to be the period t, right? So that's what I mean. So period t can be defined in many ways, but the simplest way to think about it is period t is crest to crest or trough to trough. So naturally then, t is 1 over frequency. So you can define a frequency, or frequency is 1 over t. So we can define that. We can also think about t from our earlier studies as 2 pi over omega, where omega is the angular speed. This is not w, this is omega. It's a Greek letter, omega. Omega is the angular frequency or angular speed. Remember, we did angular momentum conservation. I1 omega 1 is I2 omega 2. It's the same omega. Okay? All right. So the other thing that I want to remind you is that the energy stored, which I was writing here, we can think of it as W, let's say. Oh, let me write my W in a very distinct way. W is 1/2 k x squared. What energy is this? Potential energy. So we should write potential energy. Okay, now observe something interesting. We are starting this at the point P when it has been stretched by the amplitude A, right? I said this is amplitude A, so x equal to A, and velocity is 0. So therefore, I should be able to say that the total energy since total energy is constant, let's call it E, and total energy E at point P is going to be 1/2 k A squared plus 0, because the velocity is 0. So this is the potential energy and this is the kinetic energy. So therefore total energy at point P is this. Okay? So it then follows that the total energy at point Q, where the motion again stops because it has to now turn, must also be the same. So this therefore is also equal to total energy at point Q. Now that makes sense because it's x squared. So whether I have plus A or whether I have minus A, I get the same result, right? So this quadratic function here guarantees that whether you have a plus A or a minus A, it doesn't matter. It's going to give you the same energy. So what happens then at O, at the middle? What happens at this point? At this point, total energy at E at O, there is no potential energy because the stretch is 0. So potential energy is 0. So this is the potential energy. Plus kinetic energy must then be maximum, which means all energy must be kinetic at O after I have released it. I call it V max for now. So 1/2 V max squared in this case is kinetic energy at O. So potential energy at O. This is kinetic energy at PQ. Okay? Any questions? Be very clear in your head in this. If there is any iota of something being unclear, please ask, because this is not easy. Okay? But be very clear. I'm trying to make it as easily followable as possible, but this isn't easy. Yes? Huh? K is the spring constant. Remember, we have in Hooke's law F equal to minus kx, so K is your spring constant. Yes? A is the amplitude, correct. So A is the amplitude. A is the maximum distance that it can go either way. That's what the amplitude means. All right? So at this point, we have fixed what happens in P and what happens in Q. We have fixed what happens in O. So we are now ready to ask what happens at any arbitrary point. So this is energy E at any arbitrary point through which the oscillator moves. So at any, since energy is going to be conserved, at any arbitrary point, I have two pieces. I have a potential energy, which would be 1/2 kx squared, and I have a kinetic energy, which would be 1/2 mv squared. So that's what happens at any given point. I got to know the v and the x. If I know the total energy, if I know x, I can find v. And you will encounter quite a few problems in which you'll be asked to do exactly that. So don't get tripped up if I ask you to find v, and I give you the total energy and I give you at which point you're supposed to find v, because it just comes straight out of energy conservation. It's not rocket science. So if you know x, then this then gives you a clear relationship between in how to calculate x and v. So I can therefore write, for example, since total energy is conserved, energy at P or at Q is 1/2 k a squared, and this is equal to energy at O, which would be 1/2 v max squared. You should be able to construct these very easily by just looking at your diagram. And this is also equal to 1/2 kx squared plus 1/2 mv squared at any point along the trajectory. Trajectory meaning path of m. Right? So if I give you, for example, A, suppose I give you A, you can immediately write, suppose A is known. Some x is given. You can find the velocity at that point. What we'll do is we'll write energy is 1/2 ka squared, and then that would be equal to 1/2 mv squared plus 1/2 kx squared. So if I know A, if I know x, so if I know A, if I know x, I can calculate what v should be. Simple. And just to give you the formula, if you do the calculation, the halves go away, and the answer should be plus minus k over, this is a k over m square root, and then a square minus x square square root. So that's v. And of course v can be both positive and negative depending upon what's going on in the problem. Any questions so far? It's very simple, right? I'm just giving you total energy at P, total energy at Q, telling you this they are the same. That's also equal to total energy at O. Energy is conserved. At O, everything is Vmax. And I'm telling you, at any arbitrary point, you can use energy conservation to calculate what you wish to calculate. So let me now go a step further and try to tell you how x varies as a function of time. So first, let's write down that Hooke's law tells us f equal to minus kx, which means since f equal to ma equal to minus kx, we can write acceleration as minus k over m times x. So if I know x, that means I know a, because x and a are related by minus k over m, the multiplier minus k over m, as per Newton's second law. So this is Hooke's law for you. And this, of course, is Newton's second law. And from that you infer, if you know x, you know a. So this, by the way, is what is called an equation of motion in this case. Equation of motion for m. Obeying Hooke's law. Okay? So what is this x? Now this is where this is a 10-pound gorilla as you first start to look at it. So let me just construct a table of sorts. So I would write down time along this column here. I would write down x along this column here. I would write down velocity in the next column, and acceleration in the next column, and the total energy in this column. So you have a picture of what the system is doing. So at t equal to 0, which is the configuration I have drawn on the top left picture, at t equal to 0, my x is plus a. My v is 0. My acceleration is going to be, by Hooke's law, minus k over m times a. And the energy, since it's all potential, is half k a squared. Any questions on this? See if this is 100% clear, because you need to be clear on this. Yes?
At that point, that be at p over there?
Yes, at p.
How will the acceleration be?
How will the acceleration be?
Would the acceleration be 0?
No. Because acceleration must come from equation of motion. Velocity is 0. So what you have done is you have pulled this thing, right? You are releasing it. So clearly x is not 0. X is equal to a. So since you are releasing it, your velocity initially is 0 in this case. But given the x, there is a lot of force acting on it because they have actually pulled it, right? How will you get that force if acceleration is 0?
Okay.
You have to get it from equation. Somebody else had a question also. Yes?
Why do you have for the a, negative k over m times a? I'm sure you can multiply.
That's force. Force is ma, right? That comes from Newton's second. That's why I wrote down Newton's second law. Force is ma equals minus k. Yeah. Right. Hooke's law is always negative. So there is always a minus sign. Why? Because if I pull it this way, the force would be that way. If I push it that way, the force would be this way. The force is always opposing, the acceleration is always opposing x. I can draw it, but I'm just trying to save time and also trying to be intuitive rather than, because drawing is also not the easiest thing to do. Now, I told you that this full cycle, this starts at p, okay, this goes to Q. If you think about that oscillator picture, this is P. So this is the distance at P. This is the distance at Q. This is the distance back at P again. Distance at Q. Distance at P. That's what this X is showing to you. This is X of t, right? It's the same picture as I drew there. So this is at P. This is at Q. This is back at P. It's oscillating. So you see, right smack in the middle at O, that's this point here. So in the middle, so if this is going to be t, this point here is going to be t over 2. If this is t, this is t over 2. If this is t over 2, this is what? T over 4. Up to this point is t over 4. Any questions? So I can actually write down what happens at t over 4. Now if you imagine this oscillation happening in front of your eyes, at t over 4, what is the position? The position is at O. This is the position at O. So if the position is at O, x must be 0. If x is 0, the equation of motion tells you this x is 0, so the force is 0. If force is 0, all the energy is kinetic, so therefore you must have a Vmax here. And at this point the energy is 1/2 m Vmax squared, because all the energy at O is kinetic. So once again, I release it here, it speeds up, goes there, speeds up, comes back, and you are just taking a time trace of the displacement. X starts at A because I had pulled it to the right. It goes like that. This is the position at O, where x is 0. So all energy at this point is kinetic. So at O, it is moving the fastest. The fastest point of motion is as it overshoots the center and then comes back again to overshoot the center and so on and so forth. So this is t equal to 4. So what happens at t over 2? T over 2, by the way, it's at Q, this point. So at that point, clearly x is going to be minus a, because I've traveled all the way to the left. It's going to be a turning point of motion, v is 0. So this is going to be k over m a. So the force now is in positive direction, and this again is going to be 1/2 k a squared. That's what you got. That's your energetics of the motion. Now we have to do the difficult task of figuring out how to describe x. As a function of time. In other words, how to describe x as a function of time is the same as solving this equation of motion. Because the equation of motion is what actually I have to solve too. Now, it is easy to solve this equation in calculus. Without calculus, we'll just use intuition. It's much easier that way too. If you look at the oscillation, this oscillation, there is only one function in mathematics that describes this oscillation. Can you guess what it is? There is only one function. Very simple. Huh? No. He said parabolas. It's not a parabola. How do you describe an oscillatory function? Do any of you?
Wave.
It's a wave. What is it?
Is it parametric?
Huh?
Parametric?
No.
Is it a cosine?
Cosine or a sine? Same? Yeah, it's a cosine function or a sine function. So whenever you have an oscillation, so you have an oscillation that you are taking a time trace of, such that, let's say, it's going out like this. This is what happens if you look at waves on the top of the on the top of a lake, for example. If you look at a point, you'll find that point is going up and down. If you observe ducks, they go up and down. Ducks never really, are static because they are actually on water and the water has waves, so ducks are going up and down. So x of t, if you want to describe it, can therefore be described as, in this case, a sine some frequency, angular frequency omega t. So let's see if this works. In this case, this is not going to work because at t equal to 0, sine of 0 is 0, right? But at t equal to 0, what is your x? A. So this won't work. So what we'll do is, we'll take its cousin. And the cousin in this case is cosine, which is off from sine by a phase of 90 degrees. So cosine of 0 we know is 1. If cosine of 0 is 1, then my initial condition that I drew out there is immediately satisfied because x of 0 in this case is a times 1, and that works beautifully. So therefore this clearly would be a nice solution to my problem. Question is if this is indeed the correct solution. Why is he playing with the phone? What is he doing? What are you doing? Just get rid of your phone. Why don't you focus on this stuff? You want to take the quiz today or no? Maybe you shouldn't take the quiz today. So x of 0 therefore is a times 1. Okay? So if x of 0 is that, then we can actually use our energy conservation to do a lot of things. We can, first of all, we already know that a of t is minus k over m times a cosine of omega t. We know that. Because x and a are related by Newton's second law, right? So we can immediately infer that. How do we figure out what V is? Well, guess what? We know what V is from here. So we don't really have to do anything. I put in x equal to a cos omega t here, and I just calculate V directly from my presumed solution. So if this works, then we are in business. So let us calculate V of t as per my guess, and V of t would be plus minus k over m. So a square, I've already assumed my solution is a cosine omega t. So a square cosine square of omega t square root. So I should be able to write this as plus minus k over m. I have an a square and an a square, so I can kick it outside the root. That becomes an a. There's a plus minus already in place, so that's not a problem. So this now becomes 1 minus cosine square omega t with the square root, and 1 minus cosine square is what? Sine of omega t. You know from Pythagoras' theorem that sine square omega t plus cosine square omega t is going to be equal to 1. So if you know one, you know the other. Now how do you know that this is the correct solution? Well, you can certainly check and make sure if it's a consistent solution, and we have actually already shown it's a consistent solution because everything that we have drawn doing our thought experiment and everything that has come out here seems correct. If I assume x of t to be this, and then a of t is same phase with a multiplier, dimensions change obviously for acceleration, this is just displacement, and v of t comes out to have the opposite phase, which it should, because as you can see, when I start off, x is a, largest, v is 0. and it flips around. So that's exactly what you begin to see. So clearly you are in reasonably good shape in terms of describing the function. The question really is whether this is the correct solution or not. And the answer is we don't really know. The only way we'll know is by checking with experiment. So if there was a lab here that we were doing, I would be able to show it to you that this is indeed the correct solution. But that lab is 151, which we'll do later. But take my word that this is indeed the correct solution to the problem. So I've taken you through this whole solution, but we can actually broaden the solution a little bit, and I'm going to give you a general solution. Why do I need to give you a general solution? The reason why I want to give you a general solution is because, remember in that problem when we began today, I took the spring out to the extreme right and let it go. That was my initial condition. So that was a special initial condition I chose, where x was the amplitude and initially the velocity was 0. I started from rest. But you want your solution to be valid for all conditions, not the special condition I chose, and it's absolutely trivial to do that. All we need to do is write x of t. Instead of writing a cosine omega t, I just allow for a phase. And let's call this phase phi, where phi is an arbitrary phase. And by adding this phase, I can start my motion anywhere I want. And it changes absolutely nothing because the phase is buried inside the cosine function. So v of t then is going to be minus omega a, directly from there, sine of omega t plus phi. A of t is going to be minus omega square a cosine of omega t plus phi. But I haven't told you what my omega is. It'll turn out, if I insert my solution to the equation of motion, what pops out is that omega square, and this is very, very important. This is the connection to the equation of motion. Omega square is square root of, it's k over m. So therefore omega, the angular frequency, is square root of k over m. That's very interesting. What it's telling you is that the mass and the spring constant, these two quantities conspire to tell you how rapidly it will be oscillating. So therefore the angular frequency omega is controlled by k over m. The tighter the spring, higher the frequency. So for example, if you want to have a high frequency system, in effect what you need to do is make sure that the effective spring is very, very tight. In other words, the spring constant k is very, very large, and then you can take it to whatever frequency you want, okay? And you'll get the right result. So at this point, I want to do one more thing. Let's see, where do I, maybe I'll do it here. This is a very important chapter. Don't underestimate the difficulty of this chapter. I'll be giving you quizzes again, quizzes from this chapter most certainly on Thursday and beyond. And we will not be repeating this chapter anymore because there are things that I want to do that will require some time as well. All right, so one of the things that you get out of this study immediately is the connection with that of a simple pendulum. Of course, I don't know how many of you have seen an actual grandfather clock. Have you ever seen one? Anybody? Not too many, right? So you have seen one. Yeah, not too many people probably have seen. So grandfather clocks, in case you may have seen pictures of them when you were a kid. So it'll be a clock like this roughly, and this is where the dial is, and then this is where you can actually see a pendulum going back and forth, right? So that's your traditional grandfather's clock, and you then wind it up every 24 hours just to make sure it gives the right time. So the idea of a grandfather's clock is tied to the idea of a simple pendulum. So this is basically a simple pendulum. So if I want to draw a picture of this, so this is, let's say, where I have taken my pendulum out, right? So it turns out then that, let's say this distance here is x, okay? And the string has a tension T, and let's say this angle is theta. Then I'll have a force in this direction and a force in that direction. So this force, which would be T sine theta, would be actually, this is theta, so this is going to be 90 minus theta. So this is going to be T cosine theta, I'm sorry. So T cosine theta is going to be equal to mg. Here, the force that will be going in that direction, because you have stretched it, is going to be T sine theta. Sorry. This is I actually oversimplified it. I'm sorry. Let me fix that up. I was trying to oversimplify. Here what happens is that this is actually slightly curved up. So you have mg like this, and then you have an mg, this angle is theta. So you have mg cosine theta. So mg cosine theta balances out the tension T completely. And so what happens is that you have an unbalanced force that way. And this unbalanced force is mg sine of theta. Okay? So that's the unbalanced force. So what happens now is that my force, which will push this bob back, is going to be minus m times g sine of theta. And when theta is typically much less than 10 degrees or so, it turns out that sine of theta is roughly equal to the radian value of theta itself. So therefore, I can write this as minus mg times theta. And if this length is L, and if this is x, I can write it as minus mg. It's a little bit tricky, x over L. Okay? So therefore, the equation for a pendulum is F equal to ma and equal to minus mg x over L. So therefore I can cancel out the masses. So acceleration A is minus g over L times x. So therefore this now is going to be your omega squared. So time period t is 2 pi over omega, and therefore time period t is 2 pi over m over k. So I should have written f equal to minus or 2 pi, wait, let me, equal to 2 pi square root of L over G. So I'm not working it out completely. You can do this yourself. But the main point of the story is that when you swing this pendulum outward to the right or to the left, and if this angle is not very large, then basically what happens is that the mg can be thought of as having two pieces. One is an mg cosine theta that will balance the string tension, and the other is an mg sine theta that will be an unbalanced force. So mg cosine theta takes care of the string tension T, so that's not a problem. But mg sine theta, which is that way, becomes the restoring force that you have in the equation. So therefore, this restoring force approximately comes out to be this force here, where all I'm doing is I'm actually assuming that this arc of the circle, this arc here, can be roughly approximated by an x. So that's what we are doing. So x over L, so therefore mm cancels, so acceleration is minus g over L times x. So this therefore can be written as minus omega square x, etc. From there I get that. And omega, of course, you can construct is going to be square root of L over g. So let us stop here. This brings us to the end of simple harmonic motion. I'm going to do an exercise problem on Thursday. And after that, we will move to some other stuff. So let's go to the quiz.